Hello everybody. In last class we discussed about the reduction formula, very easy kind of formula. One was the formula of x to the power of n e to the power of ax dx. Then we got the corresponding reduction formula, and the second was the reduction formula for definite or indefinite integral, whatever we call, of the function sine to the power of n x dx. So we have an reduction formula for integral 0 to pi by 2 sine x dx in this fashion. We discussed the deduction as well. And for indefinite integral, this is the definite integral, and for indefinite integral, we have this kind of formula. You don't need to remember this kind of formula. You need to know the technique by which we deduce this kind of formula. Got it? So over here, I presented the technique of deducing this kind of integral corresponding reduction formula, and I forgot to tell you in last class that I want to keep a homework for you, that you yourself please deduce the reduction formula for this kind of integral cos to the power of n x dx. Okay, similar formula would appear, so I am leaving this deduction for you. Just in place of sin x, we have cos x, so similar kind of deduction would be there. Okay. Now, as per the syllabus, I need to consider the third kind of integral, the third kind of reduction formula. That would be the mix of sine and cosine. I need to consider this kind of reduction formula for the integral sine to the power of n, sine to the power of m x cos to the power of n x dx. And we have several reduction formula available in your book. This is one such reduction formula. Let me at first show you from the book. You see over here, this is the integral. If sine to the power of mx dx cos to the power of n x dx, if this is the integral I m comma n, okay, this is the integral I m comma n, where m n are positive integers. M and n are positive integers greater than 1. Sometimes we consider negative integers. I will come in the case when m and n become negative integers. But for the time being, let's suppose that m and n both are positive integers greater than 1. Why did we take this kind of condition greater than 1? That you will understand during the deduction process. Because we need this criteria for deduction process. So over here we suppose that the integral is I m comma n, integral of sine to the power of m x cos to the power of n x dx. And now let me show you from this portion. Over here we are first trying to deduce this reduction formula. We have two different kind of reduction formula available for this kind of function. This is one reduction formula. This is one reduction formula that I am going to show you right now, and a similar reduction formula is this one over here. If you look at the difference in between these two, you see, if you look at the difference between these two over here, the index, the second index is n minus 2 over here, but in this second formula the first index is m minus 2. What I am trying to say is that in this first formula, we have a decrease of second index from the index n to the index n minus 2. That means the second index has been decreased. However, in this formula, the first index has been decreased. Over here we have m minus 2, and on the left hand side we have m. Got it? So you need to be first very careful about your observation that which index should be decreased, and accordingly out of these two functions, one function is sine to the power of m, another function is sine to the cos to the power of n. Accordingly we need to make the computation, so that ultimately at final result the target index gets reduced. Okay, so let's first consider the first formula. Over here this is the first formula. Over here the target index is the second index. We want to reduce the second index, and how to do this one? In order to reduce this second index, cos to the power of n minus 1, you see, we need to integrate this integral by parts. Okay, so integration by parts, in the integration by parts, two functions are there. One is the first function, second one is the second function, and first function is differentiated, second function is integrated. Okay, so over here we are making a manipulation in such a way that cos function gets differentiated and sine function gets integrated. But the problem is that directly sine to the power of m x, this function cannot be integrated directly. If we want to integrate if we want to integrate something involving sine of x, in that case, you see, let me show you a rough computation over here. You see, over here, if we want to integrate this kind of formula, integral of sine to the power of say m x and in dx, this would not be directly possible. We can integrate it by certain kind of reduction formula that I demonstrated in last class. But over here we need direct integration, and that would be possible if we have certain cos of x function, because in that case if we assume that sine of x is equal to say z, then this imply hmm, then we have dz is equal to cos of x dx. So this expression would be ultimately converted into z to the power of m into d of z. Now it is integral. We can integrate it, and ultimately we will get this kind of integral, z to the power of m plus 1 divided by m plus 1. Got it? So this is a technique of integration, and therefore along with sine to the power of m x, we need to have at least one cos of x. So we are trying to compute the integral in such a manner that we get the combination of these two functions over here. So this is the combination. You see, out of cos to the power of n, we have n number of cos x. The product of n number of cos x. We are keeping one cos x separate in order to make this expression integrable, and this expression should be differentiated. So we shall consider this function as a first function and this function as a second function, so that we know that the second function is integrated whenever we perform the integration by parts. Got it? So over here we are taking this function as a first function. So what would be the formula? First function into integral of second function. This is the integral of second function. Why? Because this z is actually our sine of x. Therefore, if we now write this expression over here, this sine of x, z is equal to sine of x has to be put over here. So sine of m sine to the power of m plus 1 x should appear. So integral of this function means sine to the power of m plus 1 x divided by m plus 1. Got it? That's why we are directly writing this integral. You can directly write it over here. So sine integral of sine to the power of mx cos x, that integral would be is equal to 1 by m plus 1 sine to the power of m plus 1 x. Minus. So this is the first term over here. The first function multiplied by integral of second function minus derivative of first function. What is first function? This is the first function. So whenever cos to the power of n minus 1 is differentiated with respect to x, we shall have n minus 2 multiplied by cos to the power of n minus 2x, and again further, due to chain rule, this cos of x will be differentiated and we will have minus sine of x. Okay, so this much would be the derivative of first function, and then the integral of second function. So 1 by m plus 1 sine to the power of m plus 1 x dx. So this is the integral of second function. Got it? Now you see, we already over here we already got sine to the power of n plus 1 and cos to the power of n minus 1. So it appears that we already got this much expression, sine to the power of n plus 1 x cos to the power of n minus 1 x. This is the kind of verification that we are moving in the right direction, in correct direction. We get sine to the power of m plus 1 x and cos to the power of n minus 1 x. Although we don't have 1 by m plus n over here, but that would be managed afterwards. Just you can go through this computation. Now you see over here, this minus sign and this minus sign would together form this positive sign, and this n minus 1 and this 1 by m plus 1 is coming out of this integral sign. So we have n minus 1 divided by m plus 1, and the remaining part, that means cos to the power of n minus 2 x into sine of x, and that sine of x along with this sine to the power of m plus 1 x, they would form sine to the power of m plus 2. I am writing in a separate fashion sine to the power of m and sine square. So I am telling again that sine x multiplied by sine to the power of m plus 1 x, they would together form sine to the power of m plus 2 x, and I am writing this in a separate fashion sine to the power sine square x and sine to the power of mx. Why? Because in the next line my target is to decompose this sine square x into 1 minus cos square x. My target would be to decompose the sine square x in the next line into 1 minus cos square x. I am not changing the first term at all. This much is the change over here. Now you see, whenever this expression is multiplied by 1 along with dx, of course, we have this kind of integral. And whenever this expression is multiplied by cos square x, so cos square x along with cos to the power of n minus 2x, this will form cos to the power of n x. The sine to the power of m x is not changed at all. Just cos square x along with cos to the power of n minus 1x, they would form together form cos to the power of n x dx. Okay, and we have an advantage that this expression is nothing but the given integral. We started with this integral, that sine to the power of mx cos to the power of nx dx, and we assume that this is equal to im comma n. So on the left hand side we have im comma n, and this ultimately becomes is equal to this value. This is actually, this integral is equal to im comma n, and over here in place of n we have n minus 1. Therefore it should be this first integral. this first integral should be im comma n minus 2. So we already got an integral involving im comma n minus 2, where the second integral, this second index, has been reduced by 2. In place of n, we have n minus 2. Now on the left hand side, we actually have we actually have this im comma n. This im comma n is equal to this, etc. So now if we change this im comma n from right hand side to the left hand side, we already have one im comma n. And if we change it on the left hand side, then this negative sign will be converted into positive sign. Along with that, we have a product of this factor, this multiplied by im comma n. So if we take this im comma n common on the left hand side, we will have this kind of expression within bracket. So now this right hand side can be written in this way: this first term plus this expression multiplied by this term. And this last term has been taken on the left hand side, so we will have im comma n within bracket 1 plus m minus 1 divided by m plus 1. So this would be the expression for left hand side. Now we make this manipulation. You see, if we consider the LCM of m plus 1 plus n minus 1, ultimately on the numerator we will have m plus n. So with taking m plus 1 as equal to LCM, we will have this kind of expression. This expression within bracket will be converted into m plus n divided by m plus 1. And the right hand side is not changed at all in this line. Now if we divide the total expression by this factor m plus n divided by m plus 1, you see this m plus 1, this m plus 1 and this m plus 1 will get cancelled, and ultimately we will have 1 by m plus n. That means the division by this numerator, 1 by m plus n of this factor sine to the power of m plus 1x cos to the power of n minus 1 x dx, not dx, cos to the power of n minus 1 x only, plus n minus 1 divided by m plus n into im comma n minus 2. So you already found that although we started with this 1 by m plus n, initially we didn't have m plus n in this denominator. But over here, ultimately by computation, we get 1 by m plus. So you don't need to worry about this factor. It would automatically come. Just try to be careful about this in these powers, whether we get sine to the power of m plus 1 or cos to the power of n minus 1, etc. So try to be conscious about these powers. These corresponding coefficients will automatically be adjusted. You don't need to worry about it. Now is it clear to you? এটা কি ক্লিয়ার হলো তোমাদের কাছে? Hello?
Yes, sir.
Now we apply this formula. Let's try to apply this formula. Over here we have this formula, and if we want to evaluate this kind of complicated expression sine to the power of 4 into cos square x dx, then what we need to do over here, you see over here 4 is 4, that means sine power of the power of sine was equal to m. So over here m is equal to 4 and n is equal to 2. And if we now, after deduction, you see after deduction only this is possible, after deduction of this kind of formula or this approach, you can also go through this approach. So if you put m is equal to 4 and n is equal to 2, you will get this kind of result, 1 by m plus n, that means 4 plus 2, that is 1 by 6 sine to the power of m plus 1. m means 4, so sine to the power of m plus 1 would be is equal to sine to the power of 5x dx. And then what we have n is equal to 2, so cos to the power of n minus 1, that is 2 minus 1, that is simply cos of x dx, plus n minus 1 divided by m plus n. N means n is equal to 2. So n minus 1 means simply 1 on the numerator, and m plus n is equal to 6. And then im comma n minus 2, you will get I4 comma 0. And what is I4 comma 0? Over here you see where I4 comma 0 would be is equal to integral of sine to the power of 4x dx. So now ultimately this expression gets converted into the first kind of formula that I discussed over here, sine to the power of nx dx. So you can say, sir, in place of computing all this formula, can't we simply convert this kind of expression into multiple angles and then proceed? That is also possible, but that would not be possible if we have certain expression like sine to the power of 40x. Hmm. So for some small value of this kind of index, maybe sine to the power of 4 or cos square, etc., you can convert these expressions into multiple angles. For example, over here, you see, if you want to convert this expression into multiple angles, what would be the process? We can write this expression as sine square x, then its whole square dx. So that would be is equal to, the sine square means sine square is equal to 1 minus cos of twice x divided by 2. So that would be 1 minus cos of twice x divided by 2, divided by 2, then its whole square dx. Then afterwards you can make certain manipulations, and then ultimately you'd have cos to the power of 4 and all. So yes, that is possible, because if the index in if this power sine to the power of 4, if this is a small quantity, then this kind of manipulation is possible. But if it is a large quantity, then that kind of manipulation would not be possible, at least in exam hall. So whatever technique you want to follow, just in any of the technique, you have to ultimately compute this kind of integral. Okay, and this is one integration formula. Mostly in exam, you would not be given to evaluate this kind of questions. If it is selected to given to evaluate this kind of questions, at most you will have 2 or 3 marks. But if it is if a question comes from 5 or 6 marks, then this kind of deduction would ultimately come in your exam. Okay, so this kind of deduction would contain would have 5 to 6 marks in that question. Now suppose in place of this formula, hmm, in place of this formula, we want to compute this second formula. In place of this formula, we want to compute this second formula. Then what to do? You see, in the previous deduction, what we did in the previous deduction, we actually integrated the sine function. How we computed a sine function, sine to the power of m, along with the cos of x. Over here you see we had sine to the power of m along with the cos of x. And that's why we have larger power, sine to the power of m plus 1 after integration. In place of m, we have larger power, sine to the power of m plus 1. But over here, if you look at this expression, let me make it a bit larger. This expression over here, we have cos to the power of n plus 1x. So you see, cos to the power of n plus 1, that means cos function has to be integrated. Cos function has to be integrated, and therefore we need to make our computation in such a way that ultimately we get some functions so that we can compute this cos function. That's why we are, along with this cos function, we are keeping a sine function. because derivative of cos x is equal to minus of sin x. So derivative of cos x becomes is equal to minus of sin x, and therefore over here, if you have this kind of expression over here, you see, suppose we have simply sine of x and multiplied by cos to the power of nx. Then what to do over here? Then we should consider just similar to this process. Then we should consider cos of x. Cos of x is equal to z, so that dz is equal to minus sine of x dx, and then this expression will be equal to minus of integral cos to the power of x means z to the power of n, z to the power of n dz, and that would give us this kind of expression, z to the power of n plus 1 divided by n plus 1 along with this negative sign, and that would be is equal to cos function is cos to the power of n minus 1 x divided by, sorry, cos to the power of n plus 1 x divided by n plus 1. So you need to proceed in that fashion. Okay, so already I have demonstrated the first formula, and I am keeping this formula as your homework. You just make this formula easy, and I would advise you to please go through this kind of formula, and if you deduce this kind of formula, I would advise you to please use some loose sheet. Hmm? And throughout my course, I will keep certain formula for your homework. I am leaving this formula for your homework. Okay, I am leaving this formula for your homework, and whenever you solve this formula, you please try to solve them in loose sheets. And after solving this formula in that loose sheet, you please keep that loose sheet in a file, separate file, so that after completion of the entire chapter, you will have one more collection of solved problems as kept in a separate file, and that would help in your examination. Okay, that is my advice. Okay, so I am keeping this formula for your homework. So let's move to that remaining part of this deduction. In the previous deduction, we considered that m and n should be positive integers greater than 1. Why we considered positive integers greater than 1? Because of this kind of expression. Suppose n becomes is equal to 1. If by chance this n becomes is equal to 1, in that case n minus 1 would be is equal to 0. And if by chance n minus 1 becomes is equal to 0, then this term would not appear at all, and there would be some computational difficulty. Okay, that's why it is advised that m and n should be positive, as well as they should be greater than 1. Next, in the next portion, what we are considering over here, in the next portion, you see, we are considering m and n may be positive integers. Sorry, not this one, not this one, not this one. Over here, m and n both, or a single m or single n, either m or n or both are negative integers. That means m may be positive but n is negative. M may be negative but n is positive, or it may so happen that m and n both are negative integers. Okay, then what to do? Okay, then how to proceed, and how to get a reduction formula. We are going to show this technique, that how to proceed and how to deduce a reduction formula. We already have this kind of reduction formula, and so from this reduction formula we are going to deduce that if by chance we have one more, we have m and n, at least one of them are negative, then how to proceed? Got it? Suppose over here in this integral formula, if by chance m and n are negative, what was im comma n? Im comma n was this kind of expression. Im comma n was this kind of integral. So let me copy this integral, and in order to move first, uh, we can say if im comma n is this kind of integral, then we already got this result. Hmm? And the observation is that this second index is get reduced. Now by chance, suppose n is a negative quantity. Suppose n is equal to -3. Okay. Then using this kind of reduction formula, in that case, if n is equal to -3, then n minus 2 would be is equal to -5. Okay. You see, we get in that case higher negative but larger index, and that would make our formula much more complicated. We are trying to manipulate the integration in such a manner that higher indices becomes lower, so that ultimately we have some certain simple formula. Okay, that would be our target. The higher indices would get lowered. It may be positive, it may be negative, but higher indices would get lowered. In place of higher index, we will have lower index or smaller index. In place of larger index, we would have smaller index. That would be our target. But if suppose n becomes is equal to -3, in that case n minus 2 would be equal to -5. That means this smaller index -3 becomes is equal to larger index. Opposite category of effect comes over here. Then of course this kind of reduction formula would not be of any use at all. Then what to do? We need to we need to follow the converse approach. How to follow this one? Over here, what we are doing, we are replacing n by n plus 2. What we get? What we would get replacing n by m plus 2? What we shall have? You see, just replace this n by n plus 2. So in that case, in on the left hand side, we would have n plus 2. Got it? On this left hand side, in that case, we will have n plus 2, and this n, in place of n, we will have n plus 2. Then over here, in place of this n, we will have n plus 2 minus 1, and over here n plus 2 minus 1, n plus 2, this n will be equal to n plus 2, and this index n minus 2 over here, we shall have n plus 2 minus 2. That means simply we shall have I m comma n. Got it? And so we can say that this im comma n, over here, you see this im comma n, this im comma n would be is equal to what we are doing. We are multiplying this entire expression by m plus n plus 2, and then dividing the expression by this quantity. What is this? This is actually n plus 1. N plus 1. Got it? This is also n plus 1. N plus 1. So we are dividing the total expression by n plus 1, multiplying the total relation by m plus n plus 2. So we shall have this kind of expression. That would be m plus n plus 2 divided by n plus 1 into I m comma n plus 2 minus, because why minus? Because this term, I am considering this term on the left hand side, so this term will become is equal to would become a negative term, so minus 1 by n plus 1 into this expression. So what we observe, we can write it in this fashion. We can write it in this fashion. And over here now, if by chance n becomes is equal to minus 3 in this index, suppose n becomes is equal to minus 3, in that case, now after using this formula, n plus 2 would be equal to minus 1. So minus 3 would become is equal to minus 1, and then minus 1 would be is equal to plus 1, and so on. That means this expression would become little easier. Larger index, negative index, minus 3 was larger negative index, and now this minus 1 would be a smaller negative index. Okay, so in this way we will be able to apply the reduction formula. Our target is to make this formula or make this expression simple. Let's try to understand this by an example. Over here you see, over here we have cos to the power of 4x, cos to the power of 4x divided by sine square x. That means over here m is a negative number and n is of course a positive number. N is equal to 4 and m is equal to minus 2. So if we now apply this formula, this is the formula. So if we now apply, this is one form. This is the formula I actually deduced. Over here, the target index is the second index n plus 2. We can also have a target index m plus 2. We can adjust the manipulation in such a manner that the first index gets increased by 2. Okay, so in that case we will have this kind of formula. So over here, what would be the reduction formula? Should we use this reduction formula or should we use this reduction formula? That would be a matter of confusion. In that case, our target would be to concentrate on this negative index. Over here, m is the negative index. We need to increase this index. So we need to increase this first index m plus 2, and that's why we need to apply this formula. Got it? So we are applying this formula, and ultimately in place of in place of m is equal to minus 2, just if you put m is equal to minus 2 over here, then on the right hand side m plus 2 would be is equal to 0. So we have I 0 comma n, that means n is equal to 4. This is m plus 2 comma n, so 0 comma m plus 2 means 0 and n is equal to 4. So I 0 comma 4 would ultimately appear. Now over here you see, we have this m is equal to 0 and n is equal to 4. So n is equal to 0 and m is equal to 4. What would be the process? M is equal to 0 and n is equal to 4 means we already got these two indices non-negative. So we can apply the previous formula that I discussed. In the previous case, m and n were positive integers, non-negative integers, and therefore we can apply all this formula, and we ultimately become able to compute this I 0 comma 4 that would be converted into this kind of expression I 0 comma 2, and I 0 comma 2 can also be converted into I 0 comma 0. And I 0 comma 0 means simply that would be the integral of dx, that is actually simply x. So in this way we can compute. In exams you will get this kind of reduction formula directly. So you please practice this fourth formula. This is one formula, formula number 5.5. this formula number 5.4, and then in the previous deduction you please go through this kind of formula. What is this? This is formula 5.2, and one more formula is there, 5.1. These are all formula for indefinite integrals. Got it? But sometimes you may get this kind of definite integral. That means this limit 0 to pi by 2. And then what to do? Just in this first term, of each and every formula, you just put this lower and upper limit 0 to pi by 2. And in that case, you see over here, at x is equal to 0, sine x would become is equal to 0. So that would vanish. Again, at x is equal to pi by 2, cos of x would become is equal to 0. So that would vanish. So in any case, ultimately the total expression arising from first term will get vanished. Only the second term would be present, and the expression would be much more simple in case of definite integral. So corresponding to all these four formula, over here formula number 5.1 or formula number 5.2, and then the remaining two formula over here, formula number 5.4 and 5.5, we shall have the corresponding formula for definite integrals. Okay, so that you need to keep in your mind. You have to practice all this formula. So although it is available in this book, but you please practice all this formula. Otherwise, in exam you will get all the questions common. Okay, in exam you will get all the questions common, but if you do not have proper practice, you would not be able to show all the total deduction. That's why I advise you to practice this formula.